In the classical theory of thin plates, we have found the expression for the energy V that can be expressed as an integral over a volume. So integral d3x, and this d3x can be written as dh, where h is the distance from the neutral plane. It is something that I have discussed in the lecture, in the first lecture on the classical theory of plates. And then we're also integrating over the dx dy. This is the area, the small area, dx dy, which composes the plate. So dx dy, if we integrate over dx dy, we get the overall area of the upper part or the lower part of the plate. And then here we have the thickness of the plate, which we might call capital H. So dH is in this direction here. dH is the small element along the direction of the thickness. So this is the plate basically. And now after this we also have some constants. We have E. We also have h squared. So h squared actually is not a constant because we have to integrate over h. So the integral over h is only acting on this h squared here. We have dh h squared, and we have to integrate from minus h over 2 to h over 2 because the neutral plane is in the middle of the plate. So the neutral plane is the plane where we have no compression, or in general no deformation of the plate. So epsilon, the epsilons and the sigmas are zero there. So when we do this integral, when we carry out the integral over h, basically we get 1 over 3, and then we get h cubed to be evaluated between minus h over 2 and h over 2. So this integral will give us 2 over 3 h over 2 to the third, or if you want, we get h cubed over 3 times 8 multiplied by 2. So it's h cubed over 12. So we can put these quantities together if we integrate over h, basically. So I can do it at once. I can do it here. When we integrate over h, because all the other quantities do not depend on h, we can put h cubed here. We divide by 12, then we have 1 minus nu squared. We also have a factor of 1/2 if you check the previous expressions, and then this quantity here is called d. This is the constant d. Then we have d squared w dx squared squared plus d squared w dy squared squared. Then we also have plus 2 d squared w dy dx squared plus 2 nu. Then we have d squared w dx squared d squared w dy squared plus, and then we have actually one last term, so I can put it here. I have minus d squared w dx dx dy. This is squared. We close this bracket, and then we also close the square bracket like this. We have already taken the variation of v, and in the case of zero external forces, we can set the variation equal to 0, and we can find the so-called equations of motion in that case. But in this case, I want to be a little bit more general. So I want to recalculate this change. The change in this total energy can be written as integral dx dy. Then we have d over 2. Then when we take the variation, we have twice d squared w dx squared. We have the change in d squared w dx squared plus 2d squared w dy squared, variation of d squared w dy squared plus, and then we get 4 d squared w dy dx, the change in d squared w dy dx. Let me zoom out. So we have dy dx, or dx dy, we assume them to be exactly the same, plus 2 new d squared w dx squared, change in d squared w dy squared, plus the change d squared w dx squared, d squared w dy squared, minus 2 d squared w dx dy, the change in d squared w dx dy. So we close this bracket from here, and then we also have to close the square bracket. If you recall, in the video regarding the classical theory of plates, we had integrated by parts twice in such a way that, for example, here this would become, so this term would become 2d4 dx for w, so the second derivative operator will act on this term, and then we would be left with delta w like this. So we can do that by neglecting the boundary terms, assuming that we have no variation on the boundary. We can do that, and at the end of the day what we get is basically the equations of motion. But there are other ways to vary this action here. So you can see that in this case we have expressed our action in such a way that we have the differentials of, I mean, these are not really differentials, these are the variational changes of the second derivatives. So it's as if basically we are considering the Lagrangian to be a function of the second derivative. So d squared dw dx squared, d squared w dy squared, and d squared w dx dy, because you can see that the change contains the variations of the second derivatives. If you integrate by parts once, you can make the variational changes of the derivatives appear. So dw dx and delta dw dy, like this, if you integrate by parts once. And we can do that. So for example, we can write this in the following fashion. You have an integral over dx dy, and then you have d over 2. Then the first term can be written as minus, due to the fact that you integrate by parts once, d cubed w dx cubed. And then you have the change in delta w dx, like this. And then we can do something similar for the second term, minus 2 d cubed w dy cubed delta dw dy. And then I want to show you also why this could be important, because we can find some other equations that I can show you. And then I'm going to consider this term as given by twice the term itself. So basically twice the term itself, and then twice the same thing. So I have split this term in two parts, two equal parts. So I have 2 times this term, and then I have 2 times this same term here. And, why is that? Well, because one of them, so this one, for example, we are going to integrate by parts over y. So I can write that as minus 2 d cubed w dy squared dx, and then I have delta of dw dx. So I'm doing that for symmetry reasons. And then I can do the same thing for the other, for this one, but in that case I'm integrating by parts over x. So I have minus 2 d cubed w dy dx squared delta of dw dy like this, and then I have plus 2 nu, then I integrate this one first, so I have minus d cubed w dy dx squared delta of dw dy, and then I have minus, I have d cubed w dx dy squared delta of dw dx, and then the last term here can be, this one can be integrated by parts similarly, similarly to what we did here. I'm going to split this term in two parts. Basically, I have minus this, because you can see that we have this factor of 2. And one of them we can integrate over x, and the other one we can integrate over y. So basically, I have plus. When I integrate one of them, this minus will become a plus, and I get d cubed w dx squared dy delta of dw dy plus d cubed w dx dy squared. So in this case, I integrated over the other variable delta of dw dx like this. You can see that this will cancel this one, and then this one will cancel this one. So the expression will simplify a bit. So why am I doing this? Am I doing all these complicated calculations? Well, not really complicated, but what is the point of this? The point of this is to show you that basically the Lagrangian contained in this integral, I'm calling it Lagrangian because this can be considered as an action, even though it's really the energy, but this function inside the integral here can be considered as a function, as you can see, of the variables of the second derivatives, because when we take the variational change of the function, we have the change with respect to these variables. So, for example, if we have a function of f of xy, if we take the differential of the function, we get the change of the function with respect to x dx, and then we have the change of the function with respect to y dy. So you can see that the function depends on y and x also from the right side, because we have the differential of x and the differential of y. So we can consider the function to be a function of x and y. This means that the first part, here it's as if we are considering the Lagrangian and consider an integral of the Lagrangian, where the Lagrangian is basically this function here. This is L. So we have the Lagrangian, which is a function of d squared w dx squared, d squared w dy squared, and it is also a function of d squared w dx dy, and you have to integrate over x and over y. But at the same time, you can see below from this that it's as if we can consider the Lagrangian also as a function of dw dx and dw dy. So basically, we can consider the same integral, or maybe we can consider the variation here, the change of this Lagrangian, that's also equal to the change of the Lagrangian, as if, in this case, we can consider it as a function of dw dx and dw dy. And this is thanks to the integration by parts, which allows you to rewrite the Lagrangian in terms of other variables, as you can see. And the same trick can also be applied if you consider, if you integrate by parts another time, you can consider the Lagrangian to be a function of w, right? And what does this lead to? If we consider this change, for example, this would be an integral of the change in the Lagrangian with respect to the first second derivative, like this. Here you have the change in the second derivative with respect to x squared. Then you have the change in the Lagrangian with respect to, so let me try to use the proper symbols, delta d squared w dy squared. And then you have the change in delta square, sorry, del square w dy squared. And similarly, plus delta L, delta of d squared w dx dy. And then you have delta of d squared w dx dy. And this is the change if we consider this expression. And this must also be equal to the change if we consider this expression here. So in that case, we have the change of the Lagrangian with respect to dw dx, delta dw dx, plus the change in the Lagrangian with respect to dw dy. Let me use the proper symbols. Delta dw dy, dx dy. Now we will leave this term unchanged, but we can change this one by integrating by parts. So if we integrate by parts, and with some simple algebra, in particular, I'm going to consider this term as given by 1/2 times the term itself plus 1/2 times the term itself. Why is that? Well, because one of them I'm going to integrate by parts over x, and the other one I'm going to integrate by parts over y, due to symmetry reasons. And once I do that, for example, the first term here will become minus partial derivative with respect to x of the change in L with respect to del squared w dx squared. And I can factor out, so I can put this minus outside of the integral, basically because all these terms will change sign. So inside the integral I will consider only plus signs. Then I have plus 1/2 derivative with respect to y of the change in L with respect to d squared w dx dy. This multiplies the change in del w dx. And similarly, I have another term, so I have plus, let me put also a curly bracket here, plus I have d dy, the change in L with respect to del squared w dy squared, plus 1/2 d over dx, the change in L with respect to d squared w dx dy. And this multiplies delta of dw dy. And this multiplies dx dy, like this. Now from here we can find some equations of motion. Basically, we can set this one with the minus sign equal to this one. And similarly, this one should be equal to this one with a minus sign. And later we will come back to this. We will see what kind of equations this will give us. It's quite important because you will see that what will appear are the bending moments, the shear stresses, and also the twisting moment. Similarly, you can also write down variational changes of this kind. So you can consider the variational change of the Lagrangian as thought as a function of only w, because as I said earlier, by integrating by parts appropriately, the change inside this action here, so the change of the Lagrangian, can be written as something that multiplies the change delta w. It is something that we have already done, basically. And it was something that allowed us to derive the function, so the equation nabla to the fourth w equal to 0 in the case of no external forces. So we have the change in this integral L of w dx dy equal to the change in the integral L, and we can think of that as a function of only the first order derivatives or the second derivative. So if we consider the second derivatives, we have d squared w dx squared, d squared w dx dy, and d squared w dy squared dx dy. Now, if we rewrite the expression that we have on the right by integrating by parts twice, the equations of motion that this will lead to is something like this. We have the change in L with respect to W equal to, we have the second derivative with respect to X with respect to Y of the change in L with respect to d squared W dx dy plus second derivative with respect to X squared, the change in L with respect to d squared W dx squared plus d squared dy squared, the change in L with respect to d squared W dy squared. And this is another equation, which we can call the equation of motion. I will discuss it later. And another equation that we can derive is the following. We can consider the change, and the Lagrangian is written as a function of the derivatives dw dx and dw dy dx dy. This must be equal to the change in the action, and the Lagrangian in this case is considered to be a function of the second derivatives. It's just to highlight that we can do this kind of operations, d squared w dy squared, and there are also some meanings, some important meanings behind these equations, and that's what I want to highlight. And for now, this is mathematics, but soon we will get to some tangible meaning behind these equations. So once you integrate the second one by parts only once, because when you take the variation of this, you have the change in the Lagrangian, and that multiplies the change in dw dx, and then you also have the change in dw dy. And once you integrate this by parts once, you can also go back to the change in dw dx. So for example, when you have the change in d squared w dx squared, and you integrate by parts once, this will become the change in dw dx with a minus. So you also have to remember that you have a change in the sign. And if you integrate by parts twice, then the sign changes twice, and that means that it remains the same, because we have two minus signs that will cancel each other. It's like minus 1 squared. Now let me tell you that the result of this, once you do this variation, you get that the derivative with respect to y of the change in L with respect to the change in dw dy plus the derivative with respect to x of the change in L with respect to the change in dw dx, this is equal to minus d squared dy squared, the change in L with respect to the change in d squared w dy squared, plus minus, so let me close the bracket though, d squared dx dy, the change in the Lagrangian with respect to the change in d squared w, and then we have dx dy minus d squared dx squared, the change in L with respect to the change in d squared w dx squared. And this is another equation that we derive. Now let me use some physics, not just mathematics. In particular, if we go back to these changes that we have calculated, you can see that we have taken the variation of the action, where we expand in terms of the variation of the second derivatives, and also where we expand in terms of the variation of the first derivatives. So for example, if we want to calculate the change in L with respect to dw dy, or actually let's start with dx, dw dx, we have to use this second expression here, because this is expanded in terms of these changes. So dl over dw dx would give us d over 2, which multiplies minus 2 d cubed w dx cubed. And let me also remind you that we are calculating this change with respect to some specific values of x and y. So here you can see that we have an integral, so basically we are summing over all x's and over all y's. But since this is calculated at some specific x and y, we are only going to get the integrand at some specific values x and y. So we don't have the integral anymore. This is just some intuition. If you want to be rigorous, it's more complicated than that, because this is quite non-rigorous, but I think that this helps intuition. So we have to look at the second expression, and we have this first term because it multiplies this delta, so when we divide by delta we have this, but since this is independent of dw dx, so dw dy is independent of dw dx, so we don't get anything from this, but we do get something from this, so we get minus 2 d cubed w dy squared dx. So we can simplify by 2, and we can put the minus sign outside like this. And if you want, you can also collect a derivative with respect to x. So you can put d over dx here, and here you have d squared dx squared, and here you have d squared w dy squared, like this. So this is an expression that you get. And now let me define the physical quantity behind this. This is something that I call Tx, and this Tx is reminiscent of a shear force per unit area that we have along the x-axis. If you recall from the previous video on thin plates, dw dx is also proportional to u, the displacement along x. So when we take a variation of the Lagrangian, which in this case is some kind of energy density, with respect to a displacement along x, it's quite intuitive that we are going to get a force acting in the x direction, and this is related to shear. Hopefully it will become clearer later when we derive the differential equations for the forces along x and along y, and also moments, bending moments and twisting moments. Actually, I can also write something right now. So in particular, we have found that this derivative here can be expressed as derivative with respect to x minus the change in L with respect to the change in d squared w dx squared plus d over dy minus the change in L with respect to twice, so I have a factor of 2 here in the denominator, d squared w dx dy or dy dx. And just to remind you, we have found that in here. So basically this is equal to minus this. And it's the same thing that I have written in here. Now we can define this to be the bending moment along x. And why is that? What is the intuition behind that? It is due to the fact that the second derivative of w with respect to x squared gives us information regarding the curvature of the beam of the, in this case, the plate along the x direction. So the way it bends along the x direction. And this is related to the bending moment that we call mx. Similarly, here, we take the derivative or the variation of this Lagrangian, the change of the Lagrangian, the variational change of the Lagrangian with respect to this second derivative. The second derivative gives us some information regarding the so-called quote-unquote, it's not really proper terminology, but it's some kind of mixed curvature in the x and the y directions. So we will define this to be mxy, which is the twisting moment, which keeps information regarding both the x direction and the y direction. So from that, we also find the differential equation Tx equal to d over dx mx plus d over dy mxy. I will summarize it later. And another thing that you can do is you can calculate, for example, the change in L with respect to the change in W with respect to Y, and we define this to be Ty, similarly to what we defined above. The derivative with respect to dw dx was Tx, so this is Ty with the same interpretation, but along the y-axis. And we can calculate that by looking at this expression here. So once you do the variation, you get the same thing. You get minus d, but in this case you have the derivative with respect to y, not with respect to x. But here you have the same thing, d squared w dx squared plus d squared w dy squared. And this can also be written as the derivative with respect to x minus the change in L with respect to the change in d squared w dx dy with a factor of 2 here, the denominator, so you multiply by 1/2 basically, plus the change in y, so d over dy, minus the change in L with respect to d squared w dy squared. And similarly, you define this to be my, so the bending moment along the y direction, and similarly this is just mxy or myx, which is the same. So you get something similar to what we did earlier, and you can calculate mx, which is minus the change in L with respect to the change in d squared w dx squared. And to calculate this, you have to consider the expression with respect to the second derivatives here, so this expression here, where we expanded the change in the Lagrangian with respect to the second derivatives. The second derivatives here. So you have to consider that the second derivative is independent of this, which is independent of this. So they're all independent of each other. And once you do that, it is straightforward to calculate this derivative. This derivative gives minus d squared w dx squared plus nu d squared w dy squared. And similarly, you can calculate my, which is minus the change in L with respect to the change in d squared w dy squared, which is equal to minus d squared w dy squared plus nu d squared w dx squared. So you can see that they are symmetric. They are not equal because you can see that nu in the second, so in my multiplies d squared w dx squared, whereas in mx, nu multiplies d squared w dy squared. So they are symmetric in this sense. And finally, you can also calculate mxy, which is equal to minus the change in L with respect to the change in d squared w dx dy, And remember that you also have the factor of 2. There is some physical interpretation of this factor of 2, but I don't want to get into the details of this interpretation. If you do this calculation, you get minus d squared w dy dx, which multiplies 1 minus nu. And finally, you can also calculate the change in L with respect to w, and let me use proper terminology, dw like this. Now, if you check the steps that we did in the first lecture on the classical theory of plates, we can find that this is equal to d times nabla to the fourth w. And you have to integrate by parts twice, starting from the variation that we have here. You integrate by parts twice, and then you set the variation equal to 0 when you have no external forces. So this variation would be 0 when you have no external forces. In general, this change can also be defined to be equal to P, where P is an external load per unit area, so it's a force per unit area, it's a pressure, and it's perpendicular to the plate. So basically, you consider the same action that we considered earlier, but you have an additional term of the kind integral minus P delta W dx dy. So this is the change in the action due to this additional contribution P. You define it like this. So P is basically an external force per unit area, and it's along the direction Z, which is perpendicular to the plate. You can see it from here because we are taking the variation of the Lagrangian with respect to W. W is along Z. So that's why the force per unit area is going along Z. But if there is no external force, then this would be 0. Now, considering the equations of motion that we wrote earlier, this change, dl over dw, let me see if I have written that somewhere here. So we have this, but we also have another thing. Where is it? Let me see if I can find it. Well, you can see that this is equal to this with a minus sign, because we have minus, minus, minus. So we can write this change as minus this. It's as if we consider the change in the integral of the Lagrangian with respect to w dx dy equal to the change in the Lagrangian thought as a function of the derivatives dw dx and dw dy. By integrating by parts the second quantity, you get exactly the equations that I have mentioned earlier. So you get minus d over dy delta L delta dw dy minus d over dx delta L delta dw dx. Now, if we summarize what we did, basically we have found the following equations. We have found derivative of mx, the bending moment along x, with respect to x, plus derivative mxy with respect to y equal to tx. We have found the derivative of mxy with respect to x, plus the derivative of my with respect to y equal to ty. Then we have also found another equation, and we have found it in here, for example. This one here is equal to p, which is equal to the second derivative, the mixed derivative of this, that's equal to twice the second derivative of xy with a minus, and then here we have mxy. Then we have minus second derivative with respect to x, mx, minus second derivative with respect to y, my. We also found another expression, for instance, and in particular, if we take the derivative of these forces, we can derive the following equation from these two, but it's not the only way. So we have dtx dx plus dty dy. You can see that this can be written as second derivative of mx with respect to x squared plus twice second derivative of mxy with respect to x with respect to y, and then we have plus second derivative of my with respect to y squared, and this is also equal to minus p, as we can see from here. So we get minus p, but there is also another way to derive it, and it's from one of the Lagrange equations. In particular, let me see if I can find it. Now it's going to get a little bit complicated, but you can derive it from here, from this equation here, because this is ty, this is tx, this is minus, so with this minus would become a plus, but we have minus my, this one is equal to minus 2mxy, and this one is equal to minus mx. And this is in agreement with what we have done so far.